In this video, I will answer some of the questions, chapter 2 questions of chapter 1. Question number 17. Imagine that you attached a heavy object to one end of a spring and then, while holding the spring's other end, whirl the spring and object in a horizontal circle. Does the spring stretch? This is the question. When you whirl the spring, of course, this heavy object will start moving in a circular path together with the spring, of course. But of course, if an object is moving in a circular path, this object needs a centripetal force to keep it on the circle. So when this object is moving in a horizontal circle, the force which keeps this object in the circular path is the force applied by the spring, and this spring is going to be pulling this object towards the center of the circle. So this force in the third chapter will be studied in detail is called as spring force. Spring force and force because of the spring. And if you whirl this spring with a greater angular speed, according to the centripetal force equation, which is Fc is equal to m of the ball or m of the heavy object times radius of the circle times omega squared, if you start rotating the spring with a greater angular speed, of course, you need to increase the centripetal force. And what is the centripetal force in here? In this example, it is the spring force. So spring force must increase as well. How can spring force increases? You will learn in chapter 3 in details. If you stretch the spring more and more, so spring force increases. Yani centripetal force must increase because spring force is the only centripetal force. Spring force must increase, and spring force is proportional to amount of stretching, so which is represented by x, and which will be represented by x in chapter 3. So amount of stretching, so x also must increase. What does x increase mean? Yani the spring must stretched. So as you whirl a spring in a horizontal circle, spring will start stretching to provide sufficient centripetal force for this heavy object to follow that circular path. Why does the water remain in pail that is whirled in a vertical path as shown in figure? So this bucket is full of water. Of course, we are not talking about bottom position at the bottom, because at the bottom in all cases water will stay inside the pail. In this case, two forces will act on the water. One of them is absolutely gravitational force, always acts downward, and also water in the pail will be pushing the bottom of the pail. So bottom of the pail will give reaction to the water, which is Fn. So these two forces will be the force acting on the water in the pail as it is moving in the circular path. So as I said, in all cases, when the pail is at the bottom of the vertical path, the water will remain in the pail. But what about at the top, at this position? When the pail takes the position, the highest position of the circular path at the top, again there will be two forces acting on the pail. One force is, as usual, always exists, which is the gravitational force. We cannot remove it, we cannot cancel it. And one more force will be acting on this water, because bottom of the pail is in contact with the water inside the pail. So the bottom this time will be applying a force on the water downward. So Fn applied by the pail's bottom on water is going to be this time downwards towards the center of the circle. So assume that you are rotating this pail with a speed of you are causing this pail to follow a circular path with a speed of v. Vector sum resultant of these two forces must be the centripetal force. So at this position, at the top of the vertical path, centripetal force is going to be Fg plus Fn, because both are pointing the center of the circle, so both are providing centripetal force. And let's write Fc. Fc is equal to m of the water, v squared of the water, divided by radius of the path followed by the water and pail. Fg cannot change because mass of the water is not changing, g is not changing, but Fn can change. Because masses are constant, because r is constant, g is constant, only v and Fn can change. Yani if you increase v, Fn increases. If you decrease v, Fn decreases. We can decrease the v until Fn becomes 0. In this case, only force acting on the water inside the pail is going to be the gravitational force. Then if I write the equation for centripetal force, v minimum speed squared divided by r is going to be m times g. What does it mean? If you want to keep this water inside the pail, minimum centripetal force acting on the water inside the pail must be the gravitational force. If centripetal force is going to be less than gravitational force, this water will not stay in the pail, so it will follow a path finally, so all the water will pour from the pail. But if centripetal force is equal to gravitational force, so you can still keep the water inside the pail. So these m's will simplify. You can also say that v minimum squared divided by r is going to be g. What is v minimum squared divided by r? Which is ac. Yani another condition. If centripetal acceleration of the pail and the water is equal to g, you can still keep the water inside the pail. But if ac is less than g or fc is less than fg, so water will not remain in the pail. So other cases, what are other cases? If centripetal force is greater or equal to gravitational force. If centripetal acceleration is greater or equal to gravitational acceleration, so in this case, so water will remain in the pail. Okay, this is the answer of this question. And question number 20, comment on the statement, there is no gravity in outer space. We know that gravity is because of the mass of the planet, and this mass produces gravitational field around the object. This object can be planet, or it can be star, or it can be moon. And we know the equation for gravitational acceleration or gravity. G is equal to capital G multiplied by mass of the planet divided by radius square of the radius of the planet. But this equation calculates gravitational acceleration on the surface. Acceleration on the surface. But the question in here is not the surface in the space. Yani if you move from the surface to the outer space. So as you see, this is the radius of the planet. But when you go up to the outer space, so distance from the center of the planet increases. So say that you are at a distance of the altitude of h from the surface. In this case, distance from the center of the planet and the point in the outer space is going to be r plus h. Then if I write the free fall acceleration or gravitational field strength in the outer space, so equation for gravitational field strength in outer space is going to be capital G, mass of planet divided by distance from the center of the planet to this point, which is going to be r plus h. Because h is very big in the for outer space, because of that the denominator increases, so gravitational field strength will decrease. As you go farther and farther and farther, so denominator increases more and more and more, gravitational field strength decreases more and more, and finally gravitational field strength approaches to 0. And question number 21, explain why Earth is not spherical in shape and why it bulges at the equator. So Earth is spinning about its axis. This is the axis of rotation of the Earth, and it is spinning with some angular speed omega. And when you are at the poles in here, for example, you are standing at the poles, if you're exactly at the position of the axis of rotation, your body will not follow the circular path. So if your body is not following a circular path because you are on the axis of rotation, if an object is on an axis of rotation, it will not follow the circular path. If your body will not follow the circular path, so you don't need a centripetal force. But when you go towards the equator, so your body starts following a circle. But when you move more and more towards the equator, this radius of the circle increases. When you come in here, radius becomes, size of the circle increases, so radius becomes much greater. So size of the circle gets the maximum value when you are at the equator. Yani when you are, or any object at the equator, so size of the circle followed by this object is going to be the largest circle. Of course, largest circle means, so radius of the circular path is going to be maximum radius. Okay, assume that this mass is at these different positions have the same, are identical, m. So all of them needs a centripetal force to keep on a circular path. And let's write the centripetal force equation for a mass on the surface of the Earth. So which is, because Earth is a rigid object, I am going to use the equation mr omega squared, because I know that for a rigid object omegas are the same. So I take the identical masses at the pole at different locations, all have the same mass, and masses are equal. But so radius are getting larger and larger when you move, of the object is at the equator, for the object at the equator. So at the equator, so this force, centripetal force, becomes maximum because R of the radius becomes maximum. So F centripetal force is maximum at the equator because radius of the circular gets maximum value. That's why this maximum centripetal force must be provided by the gravitational attraction of the Earth. It is max centripetal force, increasing centripetal force. The maximum centripetal force at the equator is not provided by the Earth. In this case, instead of following a circular path, this mass at the equator will follow a a little straight line path. As a particle moves a straight line path, it moves away from the center. So as it is moving from the center, of course, the size of the circle will increase. That's why Earth will get bulged at the equator, because when for the masses, for the particles, for the objects at the equator, enough centripetal force is not provided. When enough centripetal force is not provided, because it needs a very big centripetal force, when this centripetal force is not provided by the gravity of the Earth, in this case object or particles or rocks or dust cannot follow circular path. So instead following circular path, they will follow a little straight line path. When they move straight line path according to lower inertia, so the radius of the circle will increase and they will start moving on a larger circle, which makes the Earth a little bulged at the equator. Question number 22. Because of Earth's rotation, you would weight slightly less at the equator than you would at poles. Why? So again, this is related to Earth's rotational motion about this axis. When you are standing at the poles, two forces act on your body. One force is gravitational attraction of Earth, which is Fg. Second one is because you are in contact with the surface, so there will be a perpendicular force acting on your body, which is called normal force. Two forces act on your body. When you step on a scale, when you press on the surface of a scale, you measure Fn. So you weight Fn, you measure Fn. Because your body is not following a circular path, because you are on the axis of rotation, these two forces are equally magnetic because no centripetal force is required. At the poles, Fn and Fg are equal because your body is not following a circle. If this is you standing at the equator, again two forces act on your body. One force is gravitational force Fg towards the center of the circle or center of the Earth. Second force is again normal force. Normal force is always perpendicular to contact surface. Again two forces act on your body, but this time your body is in circular motion. If an object is in circular motion, there must be a centripetal force acting on this object. And this centripetal force is the resultant of the forces acting on your body. At the equator, let's write the resultant of the forces acting on your body. So Fg is towards the center of the Earth, so it's positive. But Fn is away from the center of the Earth circle, which is negative. So this subtraction is going to be the centripetal force. Because you measure Fn when you're stepping on a scale. So I'm going to write the equation, I'm going to change this equation which calculates Fn. Fn will be taken, negative Fn will be taken to the right side. So Fc will be taken to the left side as negative. So Fn is going to be Fg minus Fc. So this is what you measure at the equator. Yeah, and this is what you measure at equator. So Fg cannot change. It is mass times free fall acceleration. But Fc right now at the equator has the maximum value. Why? Because your mass is mass, the same as the mass doesn't change when you are at the pole or at the equator. Mass is the amount of matter. M times R. R gets maximum value because as you move towards the equator, you start following a larger circle. At the equator, the circle you follow is the largest in size. That's why radius of the circle is the maximum. When the radius of the circle is maximum, because Earth is a rigid object, omegas are the same. Yani all these quantities are the same, but radius gets maximum value at the equator. That's why centripetal force, Fc, gets maximum value at the equator. maximum value at the equator. When this Fc gets maximum value, and this term gets maximum value, of course Fg minus Fc, which is Fn, must get minimum value. So that's why you are going to measure minimum weight at the equator, because centripetal force gets maximum value at the equator. Normally your weight does not change, but what you measure is changing because of the centripetal force acting on your body. And question number 24, astronauts floating around inside a space shuttle are not actually in zero gravity environment. What is the real reason astronauts seem weightless? So here is the keyword, is seem weightless. Now, no, in fact, if you are inside the gravitational field of a planet, there will be always acting a gravitational force on your body. But seem weightless or appearing weightless is the keyword in here. What does this mean, seem weightless? First, this is about how you feel your weight. How do you feel? How you feel your weight? We feel our weight by Fn. So, Fn acting on your body, makes you feel your weight. For example, look at the man sitting on the chair. In fact, gravitational force acting on this man is always, gravitational force is downward, so Fg acts downward on this man. But as this man is sitting on the surface, this man, because of the gravitational force, is pushing the table down, chair down. A chair is giving reaction on the man's body up. This reaction force called normal force. In fact, this man is feeling Fn. And Fn is felt by your body, So when you feel Fn, for a person sitting on a chair, because Fn and Fg are equal in magnitude, so Fn is equal to Fg, you are feeling exactly what your weight is. But inside the space shuttle, look at this picture. As you see, inside the space shuttle, they are not touching anywhere. If you don't touch anywhere, is it possible there can be Fn on your body? There's only Fg acting on your body. But because you are not touching anywhere, there will be no Fn on your body. You feel yourself weightless because you feel your weight by Fn. So how can we provide this? How can we make these astronauts not to be touching any surface? There is only one way. So if they are inside a space shuttle, which is diving with a free fall acceleration, which is equal to free fall acceleration, in this case, they will not be touching anywhere. So because they don't touch anywhere, so they are not going to feel their weight. So this is what apparent weightlessness or astronauts seem weightless. So if space shuttle and astronauts all fall with the same acceleration a, which is equal to free fall acceleration at that location, so in this case, these astronauts' body will not touch anywhere. They will not be in contact with any object because there is no contact between their bodies and then the surface. They will not feel a normal force. They will not experience a normal force, which means they will feel themselves weightless. And question number 25. A girl at a state fair swings a ball in vertical circle at the end of a string. Is the force applied by the string greater than the weight of the ball at the bottom of the ball's path? So vertical circle, this ball is moving in a vertical circle. This is the vertical circle. and this ball is attached to a string. So this is the string at different locations at the top, but the question is at the bottom. So when this ball comes in here to the bottom, of course this ball must be moving with some tangential speed and also angular speed. So at this position there will be two forces acting on this ball. One of them is always acts gravitational force towards the center of the earth. Second force is going to be the force applied by the string. So force by the string, which is we sometimes say tangent force. And this point is the center of the circle. So when we are calculating the centripetal force, why should we calculate centripetal force? Because this ball is in circular motion. At this position, there will be a centripetal force acting on this ball. This centripetal force is calculated by Ft, which is towards the center, that's why we write it positive, minus Fg, because Fg is in the direction away from the center, which is negative. So which one is greater, Ft or Fg? Let Ft alone. Take this negative Fg to the other side. Ft becomes Fg plus Fc. If this is a plus, what does it mean? Ft must be greater than, of course, Fg. One more thing, and most practical, at this position, at the bottom of the ball's path, the force which points to center, which is Ft, will be greater the force which is pointing away from the center. So always the force which is pointing center will be greater than the force which is away from the center. Question number 28. The tube within a washer goes into its spin cycle starting from rest. So initial angular speed is 0. And reaching an angular speed of 11 pi radian in 8 seconds. So this is final angular speed. In 8 seconds, this is delta t. So as you see, this tube within the washer accelerating. At this point, the lid is opened and safety switch turns off the washer, which means electricity will not be given to the washer anymore. The tube will slow, of course, to the rest from this angular speed, which is 11 pi, to the rest, which is 0. It slows in 12 seconds. Now, in this problem, we have two steps. First part of the problem is this tube within the washer is accelerating. Second part of the problem, the same tube, after the safety switch turns of the washer, this starts to decelerate. So now I'm going to record the given for accelerating part and decelerating part of this problem individually. For accelerating part, initially the tube is at rest. That's why initial angular speed for this acceleration part is 0. Then this tube reaches to a final angular speed, which is 11 pi radian per second in 8 seconds. And delta t for this acceleration part is 8 seconds. After this point on, this tube starts to decelerate. Now I am going to record the given for this decelerating part. So if it is decelerating, of course, this tube must decelerate from the final speed it reached in the accelerating part. That's why initial speed for deceleration part is going to be final speed of the acceleration part. So 11 pi radian per second is the initial speed, and slows to the rest, means final angular speed for deceleration part is going to be 0, and this change in the speed which is 12 seconds. Through how many revolutions? So how many revolutions is delta theta, but we will find delta theta in revolution. Does the tube turn? So during this entire acceleration and decelerating part, we should calculate what is delta theta. Assume constant angular acceleration while the machine is starting and stopping, which means we are going to use kinematic equations because constant angular accelerations, we use these four kinematic equations. Okay, delta theta in revolution is the question. That's why I have to use equation which calculates delta theta. When I check the given, I see that initial angular speed is given, final angular speed is given, delta t is given for both accelerating and decelerating part. Why don't I use the equation? Which equation? Delta theta is equal to 1 over 2 omega initial plus omega final multiplied by delta t. So this equation will help me to find delta theta for acceleration part, delta theta for deceleration part, and after that add them all, find the delta theta for whole starting and stopping part. Okay, so now let's start. Delta theta for acceleration part, delta theta, I will say this point is delta theta 1, is going to be 1 over 2. Initial angular speed for this accelerating part is 0. Final angular speed is 11 pi. Multiplied by delta t for the acceleration part is 8. So when I do this calculation, 8 over 2, this 8 and 2, which becomes 4. 4 times 11 pi, because 0 has no minimum addition. 4 times 11, which becomes 44 pi. So angular displacement during this acceleration part is 44 pi. Let's do the same thing for deceleration part. I will say this angular displacement delta theta 2, 1 over 2. This time initial angular speed is 11 pi. Final is now 0 plus 0 multiplied by time interval is 12 seconds. 12 divided by 2, which becomes 6. 6 times 11, which is going to be 66. So angular displacement as this tube is stopping is 66 pi. But I am going to calculate total angular displacement. I have to add them. Delta theta 1, which is the angular displacement during acceleration. Delta theta 2, which is angular displacement during deceleration. So 44 pi plus 66 pi, result is going to be 110 pi radian. But the question is revolution. How many revolutions? Let's convert this radian to revolution. Angular displacement in revolution can be calculated by angular displacement in radian divided by 2 pi. So angular displacement in radian is 110 pi divided by 2 pi. Pi will simplify. 110 divided by 2, which is 55. So during this starting and stopping time, so this tube within the washer rotates 55 times, 55 revolutions or rotations. Question number 29. An airplane is flying in a horizontal circle at 105 meters per second. So in a horizontal circle, an airplane is flying with tangential speed, which is given as 105 meters per second. If 80 kilogram pilot does not want the centripetal acceleration to exceed 7 times free fall acceleration, so this pilot will have an centripetal acceleration maximum. Does not want to exceed means maximum, it can be maximum 7 times free fall acceleration. What does it mean? 7 multiplied times is in here 7 multiplied by free fall acceleration 9.81. So centripetal acceleration of the pilot can be maximum 7 times 9.81. Let's multiply it. 7 times 9.81, which is going to be 7 times 9.81, which is going to be 68.7. 68.7 meter per second square. So find the minimum radius of the plane's path. What is r? So I'm going to use the centripetal force equation, centripetal acceleration equation, with t squared over r. This calculates AC, but I need to calculate r, only cross product and replace the positions of r and AC. So r is going to be Vt squared divided by AC. How much is Vt? Vt is 105 squared divided by 68.7. Result is going to be 160. 160 meters is the radius of this circular path. B. At this radius, what is the net force that maintains circular motion exerted on the pilot by seat belts, friction against the seat, or so forth? So net force maintaining circular motion is definition of the centripetal force. It's defining the centripetal force. And centripetal force is calculated by mass of the object multiplied by centripetal acceleration. So both are given, both are known. Mass of the pilot is given 80 in the problem. Mass of the pilot is 80. A centripetal acceleration can be maximum 7g, and 7g is equal to 68.7. So let's multiply them. 68.7 multiplied by 80. Result is going to be 5,496 Newton. This is the centripetal force, or the net force, that maintains circular motion of the pilot. And question number 30. A car traveling at 30 meters per second undergoes a constant negative acceleration of magnitude 2 meters per second squared when the brakes are applied. So which means if the brakes are applied, this car is slowing down. How many revolutions does each tire make before the car comes to stop? Assuming that the car does not skid and the tires have a radii of 0.3 meters. So initially speed of the car is given as 30 meters per second and undergoes a constant negative acceleration. Linear acceleration of the car is given as 2 meters per second squared, but it is because it is negative, constant negative, I will write negative 2. So negative 2 meters per second squared when the brakes are applied. How many revolutions does each tire make before car comes to a stop? And the final linear speed is going to be 0. So we will be asked delta theta in revolutions. This is an angular quantity, but all the givens are linear. Initial speed is given linear, acceleration is given linear, final is linear. So what should we do? First, let's calculate linear quantity, which is the displacement, how far this car travels before coming to rest, which is delta x. Delta x in the 11th grade you learn, which is in the 12th grade we say delta s. So let's calculate first delta x. After that, from this delta x, let's try to calculate delta theta. So we know that in the 11th grade we learned that. So final, for the accelerated motion, final speed squared is equal to initial speed squared plus 2 times a times delta x. So let's insert the given. Final is 0. Initial is 30 squared plus 2. Acceleration is negative 2 times delta x. So it's going to be, the square root of 0 is 0. Square root of 330 is 900. 2 times negative 2, negative 4. Negative 4 delta x. Go on. So this negative, take it to the left side as positive. 4 delta x is going to be 900. Divide by 4. Divide by 4. You will get the result as 900 divided by 4. 900 divided by 4, which is 225. So delta x is going to be 225 meters. So if delta x is 225 meter, and this 225 meter is taken by the car as the tire is rolling. So tire rolls a distance which is equal to 225 meters. Each tire rolls a distance which is 225 meters. Yani delta S is equal to delta X, which is equal to 225 meters. Delta S for each tire is equal to delta X of the car. So if I know delta S, so I can calculate delta theta. We know that delta theta is equal to delta S over R, which we learned in section 1. So delta S is 225. Del R is given as radius of each tire is given as 0.3. So divided by 0.3, 225 divided by 0.3, 750 radian. 750 radian. Each tire rolls an angular displacement which is equal to 750 radian. But the answer is how many revolutions? So angular displacement in revolution is equal to angular displacement in radian divided by 2 pi or 6.28. So 750 divided by 6.28, which is going to be divided by 6.28, 119 revolutions. So each tire rolls an angular displacement which is 119 revolutions. Question number 31 is similar to the previous one but in the opposite way. A coin with a diameter 2.4 centimeters dropped onto a horizontal surface. The coin starts out with an initial angular speed of 18 radian per second, rolls in a straight line without slipping. If the rotation slows with an angular acceleration of magnitude 1.9 radian per second squared, how far does the coin roll before coming to rest? So diameter is given for the coin. In calculations we don't use diameter, so we use generally radius. That's why radius must be 1.2 centimeter. So when needed we are going to use it. Initially this coin is rolling with 18 radian per second, so omega initial is given as 18 radian per second. Rolls in a straight line without slipping. If the rotation slows with an angular acceleration alpha, because it slows, angular acceleration must be negative. With a magnitude of 1.9 radian per second squared, so magnitude of the angular acceleration is 1.9. That's why angular acceleration itself must be negative 1.9 radian per second squared. How far does the coin roll before coming to rest? Before coming to rest, final angular speed must be 0. So how far represents delta x? So how far this coin move before it stops? As you see questions, again, this is opposite of the previous question. Now, quantities which are given in the question is angular quantities, but the question which is asked, linear quantity. So if I want to calculate delta S, so I have to first calculate delta theta. From delta theta, I will pass from this delta theta to delta x. So I will use again the fourth kinematic equation. In here, omega final squared is equal to omega initial squared plus 2 alpha delta theta. So final, because the coin comes to rest, final angular speed is 0. Initial angular speed is 18 radian per second squared, so squared plus 2. Alpha is negative 1.9 multiplied by delta theta. So continue. 0 equals 18. Square of 18 is how much? Let's calculate it. 18 squared is 324. 324. 2 times negative 1.9. 2 times of negative 1.9, 3.8, negative 3.8 delta theta. So we should get this negative 3.8 delta theta to the left side. So 3, it becomes positive 3.8 delta theta equals 324. Simplify 3.8 by dividing both sides. So 325 divided by 3.8, which is going to be 85 radian. So delta theta is 85 radian. From this, I can calculate delta S, because we know that delta S is equal to R times delta theta. R is 1.2 centimeter. 1.2 centimeter is equal to 1.2 times 10 to the power of negative 2 meter, because we should use in calculation meter, multiplied by 85. Let's do it. Multiply by, result is going to be 1.02 meters. Delta S is the arc length traveled or rolled by the coin. Of course, as this coin is rolling, it's also displacing. That's why the displacement of the coin is going to be arc length rolled by each coin. So 1.02 meter is the distance the coin traveled before coming to rest. Question number 32. A mass attached to 50 centimeter string starts from rest. Again, starting from rest. So omega initial is 0. By the time, if an object starts from rest, this is an accelerated motion. So in this problem, these types of problems, you have to use kinematic equations. And rotate it in a circular path exactly 40 times. 40 times 40 revolutions or 40 rotations. So delta theta is 40 revolutions in 1 minute, and 1 minute delta t, which is going to be 60 seconds, of course. Before reaching a final angular speed, what is the angular speed of the mass? Final angular speed is the question in here, omega final. So angular displacement, I can find omega final because this equation delta theta is equal to 1/2 omega initial plus omega final times delta t. This equation can help us because delta theta is known, omega initial is known, delta t is known, unknown is omega final. We can easily get it, just one unknown. First, we have to convert delta theta from revolution to radian. Delta theta in radian is equal to, we know that, delta theta in revolutions multiplied by 6.28, which means 40 revolutions times 6.28. So delta theta is going to be 40 times 6.28. It's going to be 251. 251 radian. So now we can use delta theta in radian in calculation. So this now go on. Delta theta 251 equals 1/2. Omega initial is 0. Omega final is the question, multiplied by delta t, which is 60. So 60 divided by 2, which is 30. So if I continue, 251 is equal to, no need to write to 0 in addition, so which is 30 times omega final. Divide by 30, divide by 30. So 251 divided by 30, result is going to be 8.37 radian per second is the final angular speed after 1 minute. And extended response question. Mars orbits the Sun, whose mass is 1.99 times 10 to the power of 30 kilogram, at a mean distance of 2.28 times 10 to the power of 11 meter. So let me draw the model. Sun and Mars is orbiting the Sun. So this is the how Mars revolves around the Sun. So let me show the Mars mass a little smaller. This is mass of the Mars, which is small m. This is mass of the Sun, which is the big M. So let's make it the big M. So this is mass of Sun. At a mean distance, mean separation from the Sun to the Mars is, which is the radius of the, of course, circular path. So R, and this R is 2.28 times 10 to the power of 11. Calculate the length of the Martian year in Earth say. Yani, what is the time for one revolution of Mars around the Sun? Because year means time for one revolution. Year means what? Means time for one revolution. So delta T for one revolution I will calculate. I know that omega average for any object which is in circular motion, because Mars is following almost a circular path, is going to be delta theta divided by delta T. And delta T for one revolution, delta theta 6.28. If time for one revolution is 1 year, which is delta T, I will calculate delta T. I know delta theta, which is 6.28. If I calculate first what is omega average for Mars around the Sun, and after that it will be very easy to calculate delta T. First I have to calculate average angular speed of the Mars around the Sun. So to calculate that, I am going to use the circular motion of the Mars. I know that there must be a centripetal force keeping the Mars in this circular path. Of course, this centripetal force is going to be the gravitational force, and this gravitational force keeps the Mars on this circular path. Let me write them. Fc in here is the gravitational force. This is the centrifugal Fc for Mars. Because Mars is in circular motion. Fc equation, m of the Mars, of course Mars is in circular motion, I have to use its mass, radius of the orbit times omega squared, omega for the Mars is going to be gravitational force between Mars and the Sun is calculated by universal law of gravity, capital G, multiplication of both masses, mass of Sun times mass of Mars, divided by separation between them, which is the radius of the square of the radius of the circle. And because both sides has mass of Mars, they will simplify. So I will calculate omega average. This is omega average. So I have to get this R to the right side. On the left, if it is multiplication, on the right, this R must be taken on the right as a division. So that's why omega average squared is going to be capital G. So in the numerator, mass of Sun is left. Denominator R times R squared, which becomes R cubed. So by this equation, I can calculate omega average, get the square root of the both sides. So omega average for Mars around the Sun is going to be root of G 6.67 times 10 to the power of negative 11. Mass of Sun 1.99 times 10 to the power of 30 divided by radius, square cube of the radius of the orbit, which is equal to 2.28 times 10 to the power of 11 cube. So I will get the square root of this. Let's calculate them one by one. First, let's calculate the inside the root. 6.67 times 10 to the power of negative 11 times, without bracket, you multiply the numerator all, 1.99 times 10 to the power of 30. Answer equals 1.33 times 10 to the power of 20 divided by, now get into a bracket because in the denominator there's an exponential number. You should always get the bracket if there's an exponential, even if it is cube. 2.28 times 10 to the power of 11, close the bracket, then cube it. So cube. Okay, inside the root is 1.12 times 10 to the power negative 14. After that, press the square root, push the answer. Result is going to be, so omega average for Mars is going to be 1.06 times 10 to the power of negative 7 radian per second. Now we got the average angular speed for Mars. Then I can use this equation. So let's go on. Because I will calculate delta t, change delta t and omega average. Delta t is going to be delta theta over omega average of the Mars. Delta theta for one revolution is 6.28 divided by average angular speed of the Mars 1.06 times 10 to the power negative 7. So let's calculate it. So 6.28 divided by answer, which is going to be 5.92 times 10 to the power of 7 seconds. This is delta t in seconds, but we should convert seconds to days. So delta t in days is going to be, so I have to first change this second to minute by dividing 60. Now it's minute. Minute to hour by dividing 60. Now hour. Hour today by dividing 24, because we know that every one day is equal to 24 hours. Answer is going to be 685 days. A similar question to the extended response: what data do you need to calculate orbital speed of a satellite? Now orbital speed means tangential speed. First we should know that, Vt. So when a satellite is revolving around a planet, we know satellites are revolving around planets. So this is the satellite's orbit. Of course, this satellite must be moving on the circular path with some tangential speed, which is called orbital speed in this question. And because it's more a circular path, there must be a centripetal force keeping this satellite on this circular path. This centripetal force is going to be the gravitational force Fg between the planet and the satellite. Let's show the planet's mass capital M, satellite mass is small m because it's a small in mass, and radius of the orbit followed by this satellite, which is radius of the circle, is r. So let's now write the equation for Fg, and Fg is the centripetal force in here. Centripetal force is keeping the satellite in the circular path, is the gravitational force, universal gravitational force. Centripetal force equation for satellite: mass of satellite, orbital speed squared, which is tangential speed at the same time, divided by the radius of the orbit of the circle, equals gravitational force, universal gravitational force, capital G, mass of planet times mass of satellite, divided by square of the radius of the, or separation between the planet and the satellite, or the square of the radius. So this mass of the satellite occurs on both sides. They will simplify. Because this r is denominator, this r square is also denominator, this square and r will simplify. So tangential speed squared is going to be capital G, mass of planet, divided by radius of the orbit, or radius of the circular path. When we get the square root, we will get the equation for the orbital speed of the satellite, which is inside the root, capital G, mass of planet divided by R. According to this equation, to calculate orbital speed, because G is constant, two variables to be known, which one of them is mass of the planet. Mass of the planet must be known, and also radius of the orbits. Orbits radius must be known. So according to that, the choice D is the answer in here.